All right, guys, so this is the last video, so I can't believe we're already here. So feel free to skip ahead any point during this video. You do not have to watch the entire thing. I'm going to try to get through this as fast as I can, so it's not a super long video. So if you need to rewind, fast forward, pause, whatever you need to do to kind of help you out, whatever you need to do. So let's go ahead and get started. So we're going to start off with circular motion, and I'm going to kind of go through this fast. So what direction is the car's velocity going? Okay, so velocity is always tangent to the circle. So if it's spinning around a circle like this, and let's say our cardinal directions are north, east, west, and south, my velocity is going to be going north. Okay, which direction is car's acceleration going? So acceleration is going to be always pointed towards the center. Okay, so that is going to be west. Okay, and then what direction is the car's force going? Okay, the force and acceleration are always going toward the center because force equals mass times acceleration. So if they're in the same equation, they've got to be going the same direction. So that means it's going west as well. Okay, number 4, the edge of a fan blade is rotating with a period of 0.17 seconds. What is the edge of the fan's blade's RPM? Okay, so the equation that deals with RPM is T equals 60 over RPM. Okay, so I already know my T is 0.17, so 0.17 equals 60 over RPM. Okay, number 1 algebra mistake I see is everyone wants to multiply by 60. Just switch these two. Okay, so put 0.17 on bottom. So you're going to take 60 divided by 0.17, and that gives me an answer of 353 RPMs. 5, a CD is rotating at 500 RPMs. What is the CD's period? Okay, so remember we just did that equation up here, number 4. So T equals 60 divided by 500. Okay, and that comes out to 0.12 seconds. So that's how long it takes to do one rotation. Number 6, a 0.02 kilogram rubber stopper is attached to an 87 centimeter length, okay, of string and swung in a horizontal circle, making one revolution in 1.35 seconds. Find the tension in the string. So we are looking for force. Okay, we know our T right here, and we know our mass, and then we know our radius right here. But I'm going to go ahead and convert that to meters because it's in centimeters. So 87 divided by 100 gives me 0.87 meters. Okay, and I want to know force. Force equals mass times acceleration. Okay, so centripetal force equals mass times centripetal acceleration. Okay, I don't have any of that. I've got mass, but I don't have acceleration. I know acceleration equals v squared over r. Okay, I have r, but I don't have v. So that means we got to find v. So we're going to start all the way back here. So 2 pi r over t. Okay, so 2 pi, my radius is going to be 0.87, and my t is 1.35. So that means my velocity is going to be 4.05 meters per second. Okay, so I can take that over here to AC. So I know AC equals 4.05 squared over my radius, which was 0.87. So that gives me an acceleration of 18.85 meters per second squared. Now I can bring this over here to my force equation. So this is going to equal to my mass, which is 0.02, times my acceleration, which I just got was 18.85 meters per second. Okay, multiply that out, and I get a force of 0.377 newtons. And that is my answer to the question right there. Okay, so we're moving on to number 7. Phil puts his favorite Justin Bieber disc in his CD player. If it spins with a frequency of 1,750 revolutions per minute, or RPMs, what is the period of the compact disc? Okay, so we know, remember, T equals 60 over RPM. So all I got to do is 60 divided by 1,750. And this comes out to 0.034 seconds. Okay, let's move on to here. So use the centripetal acceleration formula for the numbers 8 and 9 to determine what will happen to acceleration if the radius doubles. Okay, so if my radius goes up by 2. Okay, so the way you can do this is start off simple. Just do AC of 1 equals 1 squared over 1. Now what you can do is you can change that and it'll tell you what's going to happen. So we're going to figure out what happens to AC when I double R. Okay, so I'm going to leave velocity alone, so I'm going to leave that as 1 squared. And now my R becomes 2. So 1 divided by 2 is going to be 0.5. So that means my acceleration is going to go down by 2, or it's going to half. Okay, same thing on this one. If my velocity goes down by 2, so basically I'm halving it. So we're going to do the same thing over here. So I'm going to do the 1 squared thing. So if I were to half my velocity, so 0.5 squared, and leave my radius the same, which would be 1. Okay, so 0.5 squared comes out to 0.25 over 1. Okay, so this would be 1/4, or 0.25. Okay, so that means your acceleration is actually going to go down by 4. Okay, so that's a little trick you can do. Just use ones and then just switch one of the things. Okay, impulse. Okay, so define impulse. It is basically just applying a force over time or change in momentum. Okay, so I'm not going to write down these definition ones because it's going to take too long. So I'll just explain them and you can write them down and you can rewind it if you need to. So it is applying a force over time or change in momentum. Number 2, a golf club exerts a force of 45 newtons on a golf ball for 0.10 seconds. What is the impulse that the club gives the ball? Okay, so my equation for impulse is J equals F times T. So I already know my force is 45.0 and my T is 0.10. So all I got to do is just multiply those out, and that comes out to 4.5 newtons times seconds. That's my answer there. 3, a 2.5 kilogram ball strikes the wall with a velocity of 8.5 meters per second to the left. Pay attention, watch out for directions. I'm just going to underline left. The ball bounces off with a velocity of 7.5 meters per second to the right, so now I'm coming back to the right. If the ball is on contact with the wall for 0.25 seconds, how much force is exerted on the wall? Okay, I have mass, I have one velocity, I have two velocities, and I have time, and I'm looking for force. This is going to be your impulse momentum theorem, which is going to be that Ft equals mv, or change in v. So you can do this as Vf minus Vi. Okay, so force I don't know, so I'm going to leave it as force. My time is 0.25. My mass is 2.5. And my V final, so it came in to the left and left to the right, so I'm left going to the right, so I'm going to make that 7.5 a negative, so negative 7.5. Minus an incoming, so I'm going to make that one positive. Okay, so you got to make that one, if it's changing directions, you have to make that final one negative. So if you were to do math completely and correctly, you should get a force of negative 160 newtons. Okay, it's okay that it's negative because it's exerting on the ball and it may change directions. Number 4, the law of conservation of momentum states, so basically it states that the total momentum before a collision is the same after the collision. Your individual momentums can change, but the total momentum before and after stays the same. Okay, so if you need to go back and listen to that again, you can. Number 5, explain in terms of variables in the impulse momentum theorem how padded mats protect wrestlers and gymnasts from injury. So I'm just going to kind of explain this out. Okay, I will write out the equation for impulse. J equals F times T. Okay, J is basically your change in momentum, which is you stopping. So whether you hit pads or a floor, you're always going to stop. So J is never going to change. But what happens is when you hit the pad, it increases your time to stop. And if J doesn't change, that means force has to go down. So that's what's happening is when you increase the time to stop, you decrease the force. So number 6, when you jump off the table onto the floor on bent knees versus locked out knees, same concept. When you land on bent knees, what it does is it increases the time for you to stop and your body's going to feel less force. Number 7, a bug hits a windshield. The force exerted on the bug is greater than the force exerted on the car. Okay, this is false. They both feel the same force. Just unfortunately for the bug, it's just a little bit smaller than the car, so that's why it's going to lose that battle. 8, a bug hits a windshield. The change in velocity on each is exactly the same. This would be false. Car's not going to really change velocity at all. Okay, it'd be really marginal. Okay, but the bug is going to go from forward to backwards. I mean, it's going to die, but it's going to go from forwards to backwards, so it had the biggest change in velocity. Number 9, a bug hits a windshield. The total momentum before and after collision is the same. So remember we said total momentum is always the same before and after. This is true. Your individual momentums can change, so the bug is going to change its momentum. Okay, but your total before and after is going to stay the same. Okay, number 10, a cement truck has a mass of 1.5 times 10 to the fourth. That should be 10 to the 4 kilograms. And is moving at 60 meters per second. What is its momentum? Okay, our equation for momentum is P equals M times V. So your mass is 1.5 times 10 to the fourth times my velocity of 60. Okay, if I multiply those out, I get 9.0 times 10 to the fifth kilograms times meters per second. That's my answer. Okay, number 11, a 0.15 kilogram basketball is moving at positive 26 meters per second, is slowed to a stop, so watch out for that. That should be your V final, by the catcher, who exerts a force of negative 390. How long does it take for this force to stop the ball? Okay, I'm dealing with mass, 2 velocities, a force, and I'm looking for time. So this should be the Ft equals M Vf minus Vi. Okay, I've got a lot going on, so this is why I need this long equation. So my force is negative 390, so I'm going to plug that in. T is what it's looking for, so I'm going to leave it as T. Mass is 0.15. My Vf is going to be 0 since I came to a stop, and my initial velocity is going to be 26. Okay, so if we did your math out correctly, this should have been T equals 0.01 seconds. Okay. Moving on to number 12, name 3 conserved quantities in physics. Okay, that is going to be mass, energy, and momentum. Okay, so those are the conserved quantities in physics. 13, 2 skaters are initially at rest. They push off against each other, so they move in opposite directions. How much total momentum do they have after pushing off? Okay, so remember, total momentum before and after stays the same. So if they're at rest initially, so when they're at rest, they had 0 momentum. And then after, so when they push off, they still have 0 momentum. Okay, the reason why is that one skater is going in the positive direction and one skater is going in the negative direction, and those cancel each other out, and that gives you a total momentum of 0. So that's the main concept, is total momentum before equals total momentum after. Okay, number 14, the 65 kilogram ice skater moving to the right with a velocity of 2.5 meters per second throws a 0.15 kilogram snowball to the right with a velocity of 32 meters per second. What is the velocity of the ice skater after throwing the snowball? Okay, so this is, I'm going to show you the way I do these equations. I'm going to show you all 3 versions on 14, 15, and 16. So in the beginning, you had the skater and the snowball together, and then he threw the snowball and they separated. So this is going to be an M total, V initial in the beginning. Then they separate. It's going to be M1, V1 final plus M2, V2 final. Okay, you can do the chart method if you want to, but this is just the way I do it. So when they're together in the beginning, they have a mass of 65.15 kilograms. I just added the mass of the skater and the snowball. And they're moving to the right with a velocity of 2.5 meters per second. Okay, doesn't matter which one you pick as M1 or M2. Okay, I'm going to say my skater is going to be my M1, so he's now by himself, so 65 kilograms. And we want to know what is his velocity, so I'm going to leave that as VF. Plus my snowball, which is 0.15 kilograms, and that is moving with a velocity of 32 meters per second. So now all you have to do is just simplify this and solve for VF. Okay, so when you do this, you should get a VF of 2.43 meters per second. Okay, 15, a 65 kilogram ice skater moving to the right. So same kind of problem, except now we have a second ice skater with a mass of 65 kilograms is initially at rest. when they catch the snowball that was thrown at them. So this is the opposite. That means they were separate in the beginning. So we have an M1 V1 initial plus M2 V2 initial. Then they hit and they collide. So now the snowball is a part of the skater. Okay, so this is going to be M total V final. So it's just the opposite of number 14. Okay, so I'm going to say M1 is my skater. Okay, so my M1 is going to be 65, and that skater is sitting still, so that's going to be easy. You have an initial velocity of 0. Plus, the snowball that's coming in is 0.15 kilograms, and it's coming in with a velocity of 32 meters per second. Then they combine, so now my mass is back to 65.15, and I'm looking for VF. If you were to simplify that and get VF by itself, it should get 0.07 meters per second. Number 16, so after being struck by a bowling ball, a 1.5 kilogram pin sliding to the right, I'm just going to underline this just in case I need it. If anything goes left, I know to change it to a negative. So sliding to the right at 3.0 meters per second, collides head-on with another 1.5 kilograms that is initially at rest. What is the final velocity of the second pin if the first pin is moving at 0.5 meters per second to the right? Okay, so there's a lot to process there. Main thing we need to start by look at is they're separate in the beginning and they're separate in the end. So this is my third option. You have M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. Okay, so we're just going to start off simple. Let's just start at the beginning. I have a 1.5 kilogram pin. It is moving to the right at 3 meters per second. Okay, so there's M1 V1. And I have another 1.5 kilogram pin that is initially at rest, so that means its velocity is 0. Then they hit. What is the velocity of the second pin? Okay, so my M2 is 1.5, and I want to know what is the velocity of that second pin. In this case, it doesn't really matter since they both have the same masses, but if you get a problem where you have different masses, make sure you put the right velocity with the right mass. Okay, so I'm going to leave that as V2F. And my first pin, which is still 1.5 kilograms, is moving to the right, so it's still the right, so there was no left, so I don't have to change anything to a negative. If it was left, I would make it a negative velocity, so just watch out for that. Okay, so this is 0.5 meters per second, and that's adding those together. So if you get VF by itself, you should have a final velocity of that second pin of 2.5 meters per second. Okay, graphs. So when it comes to graphs, make sure pretty much everything you need to know is area under the curve. Okay, so I have a 3 kilogram stack of Mr. Heveron's Old Stale Jokes is moving along a frictious surface at 5.0 meters per second. Okay, so there's mass and there's my V initial, so those are important to know. How much impulse is given to the stack in the first 2.0 seconds? Okay, so I'm going to stop here at 2.0 seconds, and I'm going to turn this into triangles and rectangles. Okay, so remember the area of a triangle is 1/2 base times height, and the area of a square is just base times height. So if I find the area of the square, I have a base of 2. Okay, watch out for your boxes. Those actually go up by halves, so those don't each count as 1. So I have a base of 2 and a height of 4, so that means this is 8. And my triangle, I have a base of 1 and a height of 4, so 1 times 4 is 4, but half that is going to be 2. So if I want to know what is the impulse in the first 2 seconds, all I have to do is just add those up. Okay, so 8 plus 2 gives me 10 newtons per second. How much does a stack of jokes change its momentum in the first 2 seconds? Okay, so impulse and momentum are the same thing, so this is just going to be 10 newtons times seconds. Oops. Okay, find the velocity after 2 seconds. Okay, so you're going to use this equation here. You have P equals M times VF minus VI. Okay, you're going to use this equation every time. So my momentum in the first 2 seconds is 10. I just solved that. Okay, so if I were to ask in 5 seconds, you would just use the whole graph as P. So find the area under the whole curve and use that as P. Your mass is, we already gave it to you back up here to the top, was 3 kilograms. Final velocity, I don't know. That's what I'm looking for, so I'm going to leave that as VF. Okay, that was a horrible VF. Okay, minus my initial velocity, which was 5 meters per second. Okay, so make sure you cross multiply. So this becomes 10 equals 3 VF minus 15. And then get VF by itself, and you should get a V final of 8.3 meters per second. Okay, moving on to work and energy. A child is moving at a constant velocity and carries a 2 Newton ice cream cone at a constant 1 meter height above the surface level. What is the net work done? Okay, so since I'm holding the ice cream tongue twisted. Since I'm holding the ice cream cone at a constant level, okay, and I'm not actually lifting it and changing it any distance, there is no work done. Okay, so in order for work to be done, you have to be actually lifting it or moving it a certain distance instead of just holding it in the same spot. Okay, so there's 2 scenarios where work's not done. One is no distance covered. So this would be like me pushing on a wall. Okay, if the wall's not moving, I'm technically not doing any work. Number 2 is a circular motion. Okay, so there is no work done in a circular motion because your force and your distance are perpendicular, not in the same direction. Number 2, what type of energy forms increases as a pencil is falling from a desk? Okay, this is going to be kinetic energy. So kinetic deals with velocity. So as you're falling, your velocity is going up. What type of energy stays the same as a pencil is falling from the desk? That would be mechanical energy. Okay, mechanical is your total energy. Okay, so the total energy you have before is the total energy you have after. So mechanical does not change. It just shifts between potential and kinetic. Okay, so potential deals with height. Okay, so the higher you are, the more potential energy you have. Number 4, what is the kinetic energy of a 135 gram baseball thrown at 40 meters per second? Okay, so KE equals 1/2 mv squared. Okay, first I'm going to do is I'm going to fix that mass. I need to get that in kilograms. So you're going to do 135 divided by 1,000. That gives me 0.135 kilograms. So now I need to plug it in. 1/2 my mass, 0.135, times my velocity of 40. And that is squared. Don't forget that. Okay, that should come out to 108 joules. Okay, number 5 and 6, I'm basically, for these next defined ones, I'm just going to explain what they are, and you can just kind of write them down. Okay, 5, so define kinetic energy. It is energy defined by its mass and velocity. It has to have motion. 6, define the potential energy. Energy defined by its mass and height or position. Okay, so the higher you are, the more potential energy you have. The lower you are, the less. 7, define power. Rate of work being done over time. Okay, so it deals with work and time. Your equation for that. So I can just give you the equation. So I know KE equals 1/2 mv squared. Potential energy is PE equals mgh. Power equals work divided by time. And work is a force applied over a certain distance. So work equals force times distance. Okay, number 9, the law of conservation of energy states that the total number of energy in a closed system, it will remain the same throughout. Okay, so the total energy you had at the beginning is going to be the total energy you had throughout the entire thing. Okay, so number 10, an 8 kilogram bag of oranges drops a distance of 12 meters. What is the kinetic energy of the bag just before it reaches the ground? So that means when it was sitting here before it fell, okay, it had potential energy. Okay, so my potential energy equals mass, which is 8, times gravity, which is 9.8, times my height, which is 12 meters. Okay, so that means my potential energy at the top, okay, comes out to be 940.8 joules. Okay, so if it was not moving at the top, that means that's also my mechanical energy. And we know when it hits the ground, Okay, it better have the same energy. When it hits the ground, it's going to have purely kinetic energy. So my kinetic energy when it hits the ground would be 940.8 joules. Okay, this is an example of PE plus KE equals PE plus KE. So when it was sitting before it fell, it had purely potential and no kinetic, so you can cross off kinetic. And when it hit the ground, it had no potential energy anymore. It was just pure kinetic. So that's why we can set them equal to each other. 11, a motor uses 300,000 joules of energy in 1 minute as a 750 kilogram car accelerates at constant rate from rest. Calculate its final velocity. Okay, so this is going to be work right here. Time, which I'm going to convert to seconds here in a second. Okay, I have a mass, and then I'm accelerating from rest, so I have a v initial, which would be 0, and I'm looking for final velocity. The equation you're going to use for this is work equals 1/2 mv final squared minus 1/2 mv initial squared. Since I started from rest, my VI is going to be 0, so you honestly don't even have to do this part of the equation. Okay, so you're going to do 300,000 equals 1/2 my mass, which is 750. Okay, and my V final squared, I don't know, so I'm going to leave that as VF squared. So you're going to get VF squared by itself, and then don't forget when you want to get rid of a squared, you have to square root. So your final velocity should be 28.3 meters per second. Okay, so I didn't have to use time in that first one, on that 11, but I'm going to use it on this one. Okay, because it says how much power did the motor use in watts and horsepower. Okay, so I know power equals work divided by time. So you're going to do 300,000 divided by your time, which is 1 minute. I'm going to convert that to 60 seconds. And when you divide these out, you get 5,000 watts. Okay, so there's part of my answer. My first answer wanted in watts, but it also wants in horsepower. So there are 746 watts in 1 horsepower. So all you got to do now is just divide by 746. And that is going to come out to 6.7 horsepower. Okay, 13. Ball is rolling at a speed of 20 meters per second at the top of a 10-meter high hill. If it continues to roll without losing energy due to friction, what speed will it have when it reaches the top? Okay, so I have basically a smaller hill, and then I go to a bigger hill. So this is at point A, and this is at point B. So this is going to be the PE plus KE equals PE plus KE. Okay, so I can't cross anything off because I have height in both situations, so I can't cross off any PEs. And they're moving in both situations, so I can't cross off any KEs. What I can do is, I know that mass is the same throughout, so you do not even need mass. So this would be gravity times height plus 1/2 v squared equals gravity times height plus 1/2 v squared. Okay, the left side is going to be point A, right side is going to be point B. So I'm just going to plug in what I know. So gravity is 9.8. Your height on the left side is going to be 10 meters. And it is moving at 20 meters per second, so that's 1/2 20 squared. On the right side, gravity is 9.8, but now my height is gone to 20 meters. And I don't know velocity, so I'm going to leave this as 1/2 v squared. So you're going to get v by itself. Okay, and when you do, you should get a velocity of 14.3 meters per second. 14, a rifle can shoot a 5-gram bullet at a speed of 965 meters per second. Calculate the kinetic energy. So first thing I'm going to do is I'm going to convert that grams to kilograms. So 5 divided by 1,000 gives me 0.005. So kinetic energy equals 1/2 mv squared. So 1/2 my mass, which is 0.005. And my velocity is going to be 965 meters per second squared. So all I got to do is solve that out, and you get 2328 joules. Okay, so if I am going too fast, please don't hesitate to pause it, rewind it, whatever you need to do. Okay, I'm just trying to get through this as quickly as possible. 15, so same problem. So suppose it's fired straight up at the maximum height. How much potential energy does it have? So when it left the gun, that was my total energy, my mechanical energy. Even though it was kinetic, I technically really didn't have any height yet in this situation, so that is my mechanical energy. So when it reaches the top, it better have 2328 joules at the top as well. So same problem if you want to know the maximum height. Okay, so at the top I have potential energy, so I'm going to set that equal to mgh, so 2328 equals your mass, which is 0.005. Gravity is 9.8, and height I'm going to leave it as h because I don't know. And you get a height of, you're going to get a really big number here, 47,510 meters. Okay, 17, a boy throws a baseball up in the air and reaches a maximum height of 37 meters. Calculate the impact velocity as the ball hits the ground. Okay, so this is going to be a 2-point problem as well. So you have the ball in the air, and then you have the ball when it hits the ground. So this is going to be PE plus KE equals PE plus KE. Okay, so I'm going to say the left side is going to be my top, and the right side is going to be my bottom. Okay, so at the top, I don't have kinetic energy, so I can cross that out. At the bottom, when I hit the ground, I no longer have potential energy, so I can cross that one out. So this becomes PE equals KE. So remember, mass does not matter because it's on both sides. It would just cancel out anyway. So this would be GH equals 1/2 V squared. So gravity is 9.8. My height is 37 meters. That equals 1/2 V squared. Okay, so just solve for V, and you should get a velocity of 26.9 meters per second. Okay, number 18. The height to which a 50 kilogram object must be lifted to increase its potential energy by 5,000 joules. Okay, so it gave me potential energy. So I'm going to do 5,000 equals mass times gravity times height. So my mass is 50. Gravity is 9.8. And my height, I'm just going to leave it as h. Okay, just get h by itself. Get h is 10.2 meters. Okay, number 19, a 27.44 Newton bowling ball is lifted to a height and given a potential energy of 22.4 joules. Okay, this means the height is approximately, so again, I was given potential energy, which is 22.4. Okay, so this right here, when I give it to you in newtons, this is mass times gravity. Okay, so I can just plug that in for mg. So that's 27.44, and I don't know height, so I'm going to leave it as height. Okay, so get h by itself, and you get a height of 0.82 meters. Okay, 20, Ralph, a 90 kilogram boy, can run 10 laps per hour around a circular track of a radius of 120 meters. His work is approximately, so remember, if you're going in a circle, you are not actually doing any work. Okay, so that's kind of a conceptual problem. Number 21, I wasn't sure about this problem. It says if a 10 kilogram box is lifted 2 meters, how much power is exerted? Power is work divided by time, and they didn't really give us time here, so I am not really sure. Might have been a little bit of typo here, or I'm just looking at it wrong. So on that one, you might have to ask them about that because there should be a time in order to find power. 22, what constant force is required to stop a 5,298.42 kilogram car traveling at a velocity of 3.6 meters per second in a distance of 86.4 meters? Okay, you have a lot going on here, so I'm going to kind of give you this equation. Just use this if you have all this. So force times distance, which is work, equals 1/2 mv final squared minus 1/2 mv initial squared. Okay, so I'm looking for force, so leave it as force. My distance is 86.4 meters equals 1/2 mv final squared. So my mass is 5,000. Let me fix that. Okay, my mass is 5,298.42. And I'm coming to a stop, so that means my final velocity is 0. So I honestly didn't even have to write all this out because it's just going to be 0. Minus 1/2 my mass, which is 5,298.42. Okay, and my V initial is 3.6, and that is squared. Okay, so now all I gotta do is just solve for F. Okay, so when you do this, you should get a force of negative 397.4 newtons. Okay, it is fine that it is negative because it's actually stopping you. 23. Okay, a car is traveling at 65 kilometers per hour and is brought to rest in 75 meters. Assume that same conditions hold for each case. What would be the stopping distance for a speed of 130? So since my velocity doubled, okay, when you look at kinetic energy, it is 1/2 mv squared. So if I were to double velocity, that means it's actually going to quadruple the kinetic energy, okay, because it's squared, meaning that's going to quadruple the distance it would take to stop. So you take that 75 times 4, and that comes out to 300 meters. So now it takes 300 meters to stop. A 5-kilogram pellet is placed in a barrel of a toy gun and is propelled by a spring of a force constant of 50 newton meters that is compressed 20 centimeters and then released. What is the potential energy of the pellet while it's compressed? Okay, so potential energy of a spring is PES equals 1/2 kx squared. Okay, so 1/2, K is your spring constant, which is 50. Okay, X, okay, I cannot have this as centimeters, so I'm going to go ahead and fix that. So take 20 divided by 100. That gives me 0.20. So that is X, how much I actually compressed or stretched my spring. Okay, so now I'm just going to plug in, and so this comes out to 1 joule. Okay, we have another graph problem. So basically same concept here. So we're looking at area under the graph. Okay, don't forget the stuff that they give you up here. You have a mass 3 kilograms and initial velocity of 5 meters per second. Okay, so how much work is done on the stack of jokes in the first 2 meters? Okay, so again, you're going to break this up, okay, into triangles and squares. So you get 8 and 2. Okay, so how much work is done in the first? So you just do 8 plus 2, and that gives me 10 newtons times meters. Okay, what is the change in kinetic energy in the first 2 meters? Okay, so work, change in kinetic energy, potential energy is all area under the graph, under the curve. It would just be the same, 10 newtons meters. Okay, so final velocity. Okay, so when you do this one, final velocity after 2 meters, this is when you do KE equals 1/2 mv final squared minus 1/2 mv initial squared. Okay, so my kinetic energy in the first 2 meters was 10. Okay, so 1/2 mv final squared. I'm looking for final velocity. So it's going to be 1/2 my mass, which was 3 kilograms. Final velocity I don't know, so I'm going to leave it as VF squared. Minus 1/2 my mass, which is 3. And my initial velocity was 5. And that is squared. Okay, so you're going to get VF by itself, so it's going to take a little bit of algebra there. So if you do it correctly, you should get a final velocity of 5.6 meters per second. The final velocity at 5 meters, so what I'd do is just find the area of the rest of the curve. This comes out to be 12 if you did 1/2 base times height of that triangle. So that means my total kinetic energy is going to be 22. And it's just going to be the same thing. 1/2 my mass, which is 3, V final squared, I don't know, minus 1/2 my mass, which is 3, and my V initial is still 5, and that's squared. So you're going to get VF by itself, and if you do it correctly, you should get 6.3 meters per second. Okay, so you're not getting that, just check your algebra and make sure you're doing everything correctly. Okay, moving on to waves. So we're trying to kind of cruise through this, so hopefully we can kind of get through this fairly quickly. Describe 2 characteristics of a sound wave. So one is they're longitudinal. Okay, meaning that your waves compress and stretch. So it's kind of look like this. Okay, so they compress in the middle and then stretch out and then compress again. Okay, and they are mechanical. meaning that they have a medium. Meaning a medium is like air, water, or rope. Okay, you need a substance. 2, describe the characteristics of a light wave. Okay, they are transverse. Okay, meaning that they do this, look like a typical wave. And they are electromagnetic, so that's an EMR wave. Okay, and that is no medium needed. So it does not need a medium at all. Compare the speed of a wave of visible light to the speed of a radio wave. Okay, here are your EMR waves. You have radio. Okay, you have microwave. You have infrared. You have visible light, which is all your colors. You have UV light. You have X-ray. And then you have gamma. All of these have the same speed. All have the same speed. Okay, so it does not matter if it's visible light versus a radio wave. It travels at the exact same speed. The only thing that differs is frequency and wavelength. Number 4, the distance from C to G. So right here to here, that is one full wavelength. Remember, wavelength is your upside down Y. You have to have one full crest and one full trough to be a full wavelength. Number 5, the diagram given represents a blank wave. This would be a transverse wave. 6, as the frequency of a wave increases, velocity will stay the same. Okay, so you can adjust wavelength and frequency all you want. That does not affect the velocity. Velocity only changes with a change in medium. Okay, so kind of bear with my handwriting there. I'm writing in a weird position right now. So velocity only changes with a change in medium. So meaning that you went from like air to water or a thick rope to a thin rope. Okay, 7, what will happen to wavelength of a wave if frequency doubles? So frequency and wavelength are inverse. So that means if one goes up, the other one goes down. So if my frequency goes up by 2, my wavelength is going to go down by 2, so it's going to half. Number 8, when a wave reaches a free end or a less dense medium, the reflective wave will invert. Okay, so this one is going to be true. Okay, so if you go to a free end or less dense, so if you go from more dense to less or free, okay, it will not invert. Meaning it will come back in the same direction. Okay, when you go from less to more or a fixed end, when it hits that, it will invert and come back in the opposite direction. Number 9, define a wave. It is a transfer of energy in the form of a disturbance through a medium. Okay, so basically it's just energy being moved from one particle to the next, and that's how it's transferred. 10, give 3 examples of electromagnetic waves. So I already gave you those. That was radio, microwave, infrared, visible light, UV, X-ray, and gamma. Okay, so those are all types of EMR waves. 11, give 3 examples of mechanical waves. So basically anything that needs a medium. Okay, so this would be like sound. Sound needs air or water. So water would be a mechanical wave, like a rope. Making a wave on a rope, that'd be another one. So, or a spring. There's multiple options there. Describe how transverse waves and longitudinal waves are different from each other. Okay, so when you have longitudinal, meaning that they stretch and then compress and then stretch back out again. Okay, the particles and the direction of the waves are parallel. Okay. My handwriting is not the best in this video. Okay, so the particles is moving parallel to the direction of the wave. When you have a transverse wave, okay, your particles are actually going up and down, but the direction of the wave is going left to right. So these are going to be perpendicular. Okay, so that's the main difference between a transverse and longitudinal. I don't know how I just kept messing up that perpendicular. Okay, so moving on to the next. Okay, so on this, how many nodes are visible if we look at this? So I have a guy basically making a wave with a fixed end. Okay, so your nodes are going to be in the center where it cancels out. So I have 1, 2, 3, 4 nodes. And then antinodes are going to be at the top and bottom. So you don't have to count top and bottom as 2. Okay, it can just be 1. So this one I actually have 3. Okay, a wave front. Okay, so I'm going to kind of explain this is the surface on which all points are in phase with their motion. Or that's just fancy for saying wave fronts are basically just going to be like your ripples. Okay, a wave ray is the direction of a wave. So if I were to basically have my ripples like this, and if I were to add an arrow going this way, that is my wave ray. Okay, so 17. If the solid lines are crests and the dashed lines are troughs, describe what constructive and destructive interference looks like. Okay, so when you have here, you have a crest and a crest meet, and a trough meet, and a crest and a crest meet. So basically, if you have two of the same hitting each other at the same time, that is constructive. Okay, if you have, meaning basically they're just going to make each other bigger. So a crest and a crest is going to make a bigger crest. A trough and a trough is going to make a bigger trough. When you have a crest and a trough meet, so a solid line and a dotted line meet, these are going to try to cancel each other out. So that is called destructive interference. So basically, they are trying to cancel each other out. Okay, number 18, the law of reflection states that the angle of incidence is equal to the angle of reflection. So whatever angle it came in at, okay, so if I have like a surface and I'm bouncing something off, okay, the angle that it came in at is going to be equal to the angle it goes out at. Number 19, what wave property does this diagram represent? Okay, so when you have sound waves that reach an object or an opening, okay, this is called diffraction. So whenever they go through the opening, they will spread out after. 20, what does amplitude of a wave represent? That is energy. 21, what type of interference is produced when these two waves superimpose? That's just a fancy word for meet, what happens when they meet. So if I have a positive and a negative meeting, okay, they're going to try to cancel each other out, so that is going to be destructive. Okay, here I have a positive and a positive. They're both in the same direction. Okay, so when they meet, this is going to be constructive. So they're just going to make each other bigger. Okay, 23, what happens to the incident wave when it reaches a more dense medium? Okay, so that means you are going to have partial transmission. Okay, so part of the wave is going to go through the medium, and then you're going to have partial reflection. So part of it's going to come back. And when you go from less dense to more dense, okay, the reflected is going to be inverted. Okay, so reflected is going to be inverted. 24, what happens to the incident wave when it reaches a less dense medium? So same thing, so partial transmission and then partial reflection, but now it's going to be in the same position coming back. So that means it's going to be not inverted. Okay, 25, a physics student notices 30 waves arrive at the beach every minute. What is the frequency of the wave? Okay, so here's something good to write down. So you can do frequency equals waves divided by time. Period is the opposite. Okay, so if it asks about period, you could do this. You would do time divided by waves. But in this case, it wanted to know frequency. So my waves is 30. And this gave me 1 minute, so I'm going to change that to seconds. So 30 divided by 60. And that gives me 0.5 hertz. Number 26, the distance from the student to the wall is 9 meters. He is shaking the rope 6 times per second. How long is the wavelength? So basically, I want to know how long is one wave. So basically from his hand, I'm going to follow this. I'm going to kind of highlight it. Okay, so one wavelength would be right here. Okay, so this means that I basically have 1.5 waves in this total distance. Okay, so I'm going to take my distance, so 9 divided by 1.5, and that gives me a wavelength of 6 meters. Okay, 27. So radio stations are usually identified by their frequency. One radio station in the middle of the FM band has a frequency of 99.0 megahertz. As it travels from radio transmitter to your car, the sound coming out of the speakers in the car have a frequency of 200 hertz. What is the wavelength of the wave sent from the speaker to your ear? Okay, so the way you need to do this is you need to keep things separate. You have EMR side to this question, and you have a sound side to this question. EMR waves all travel at the speed of light, which is c equals 3.0 times 10 to the 8th. Okay, and then your frequency on the EMR side is, with the actual radio wave, is 99.0 megahertz. So my frequency is 99.0. I got to change that to hertz. Mega is 10 to the 6, so just add 10 to the 6 to the end of that. Okay, and then it says I have a frequency of 200 hertz, so that's my frequency over here under sound. And then velocity of a sound is normally 340 meters per second until we get further in where you can actually calculate it by temperature. But for now, it's just 340. Okay, what is the wavelength of a wave sent from the speaker to your ear? So it's asking about sound. So I'm not going to use this left side yet. I'm going to use this right side. I know velocity equals frequency times wavelength. So my velocity is 340. My frequency is 200. And wavelength, I'm going to leave it as upside down y. So get y upside down y by itself, and you get a wavelength of 1.7 meters. Okay, 28, same question. So, but now it asks, what is the wavelength of the radio wave sent from the transmitter to your radio? Okay, so now I'm actually doing with that EMR side. So this is where you do C equals frequency times wavelength. So it's going to be 3.0 times 10 to the 8th equals my frequency, which was 99.0 times 10 to the 6th. And wavelength, I'm going to leave as upside down y. Just a tip on your calculator is when you have these scientific notations, I usually put everything in parentheses, okay, because sometimes your calculator can get confused. If you don't put it in parentheses, it'll do the order of operations wrong. Okay, so if I do this correctly, I get a wavelength of 3.03 meters. Okay, number 29, the change in direction of a wave when it encounters an obstacle or an edge. This is called diffraction. Interference that decreases amplitude, this is destructive. 31, a pattern of vibration that resembles a stationary wave. Stationary means standing still, so there's your hint that this would be a standing wave. Okay, so it basically means it looks like this. You have a wave doing this, and then you have another wave basically coming back and canceling it out. Points in a standing wave that have no vibration due to destructive interference. Okay, this is a node. So remember, your nodes were at the center where everything cancels out. So a node would be like right here. The bouncing back of a wave when it meets a surface or boundary, this is just reflection. That one's pretty self-explanatory. Interference that increases amplitude, this is going to be constructive. 35, the bending of waves as they pass from one medium to another at an angle. Okay, this is refraction. Okay, so this is why, like if you put a pencil in water, that's why it looks like it's broke or bent. Okay, so when light goes from one medium to another, it bends, and that's called refraction. All right, so waves 2, so we're almost there. Okay, so kind of hang in there with me. So what occurs when an incident ray encounters a new medium at a boundary before it reaches a critical angle? Okay, so same thing. This is partial transmission. So it means part of it's going to go through. And then part of it's going to bounce back. So this would be partial reflection. Okay, your critical angle is, there is a max angle where it will no longer go through. Okay, so it will not go through, so it's going to purely reflect. Okay, so that is your critical angle. 2, which of the following objects reflect light? So you're looking for something that reflects light, not emits it. Okay, so basically anything that's not emitting light or has color, that's part of absorbing and reflecting light. So that would be something like your chair, the desk, the floor. The moon is reflective. Which of these emit light? That'd be a light bulb, the sun, and an LED screen. Okay, define the index of refraction. So your equation for this would be N equals C over V. Okay, so basically it's the ratio of the speed of light, which is your C. Okay, in a vacuum, for the speed of light in another medium. So there's your velocity in another medium. So basically it's just C is your speed of light, so that is the perfect speed. So that is at nothing getting in the way. And then velocity is going to be what the velocity of that wave is when you enter another medium, like another material. It's going to slow it down. Okay. Number 5, if it's 12 degrees Celsius at sea level, what would be the Mach number at an aircraft going 1,020 meters per second? Okay, so Mach is just basically how many times faster are you going than the speed of sound. So what we need to do is we need to find the speed of sound at that temperature. So you're going to do velocity equals 331.5 plus 0.6 times whatever your temperature is, and our temperature was 12 degrees. Okay, so that means it's going to come out to be 335.7 meters per second. Or I'm sorry, 338.7 meters per second. Okay, so that is Mach 1. That is the speed of sound. So if I want to find out how many Machs this plane is doing, okay, you're going to take that 1020, divide it by Mach 1, which is 338.7. That means this plane is pulling just over 3.01 Mach. Okay, number 6. A hiker is visiting a Grand Canyon. While in the canyon, they stub their toe and yelp in pain. The hiker hears an echo 1.22 meters per second later. If the temperature is 22 degrees Celsius, how far away are the canyon walls? Okay, so it gave me temperature, and we're talking about sound, so we're going to go ahead and do velocity equals 331.5 plus 0.6 times my temperature, which is 22. And you get a velocity of 344.7 meters per second. Okay. And then we're going to do this velocity equals distance over time. We're looking for how far they are away. So your velocity is going to be 344.7. Distance, I don't know. And remember, this is an echo. You want to know how far it takes the sound to get to the wall. Okay, so you're not going to use your total time. You're just going to half that time. Okay, so if you half that time, it should come out to 0.61 seconds. Okay, multiply both sides by 0.61. So that means the walls are going to be 210.3 meters away. 7, what is the critical angle for a light passing from glass to water? Okay, so your equation for critical angle is going to be inverse sine. So let me fix that. Inverse sine, that's just second sine on your calculator of your refracted index, so whichever one it goes to, and over your incident index. So I usually just say the I means incoming. Okay, so if I'm going from glass to water, okay, so you should have the chart. Okay, water has 1.33 index of refraction. So what I would do is I would do inverse sine. I'm going from glass to water, so that means glass is going to be my NI. That's my incoming. Okay, so I'm going to put 1.55 on bottom. I'm going to water, so this is going to be 1.33 on top. Okay, so if you're in degree mode, make sure you're in degree mode. This should come out to 59.1 degrees. Okay, so that is your critical angle. Okay, and then also I have these down here if you need to. I've got these, where I'm getting these numbers from right here, the index refraction is this chart right here. So if you need to write these down or whatever you need to do, that's fine. Okay, so what we're going to do is we're going to finish up by going into that sound and light review, since I think that's a good chunk of this exam. Okay, so not too much left, so kind of hang with me. Okay, as I scroll through, it looks like a lot more. Okay, so I'm going to try to get through this as quickly as I can. Some of this I'm not going to write down. I'm just going to try to save time. What type of a wave is a sound wave? We've been over this. This is a longitudinal, and it is mechanical. Okay, so it means it compresses and stretches, and it needs a medium. 2, what is the source of energy of all sound waves? Okay, it's just a vibration. Okay. Vibration is basically just a transfer of energy from one particle to the next. 3, what wave property is responsible for pitch and loudness? So pitch is going to be your frequency. Loudness is your amplitude. So when you hear crank the amps, like at a concert, okay, amps are going to affect your loudness. 4, explain resonance. Okay, so resonance is the increasing of amplitude, which is a constructive interference, due to a periodic force that is at the same frequency as the natural frequency of a vibration or oscillation. So the reason why this happens is if you were to, like opera singers, what they're doing is they're creating constructive interference from their voice by matching the frequency of the glass. So whenever those two forces meet, they get bigger. Okay, so it has to be the perfect frequency. And when they do that, the glass cannot take that amount of energy. So that's why it breaks. Okay, so basically resonance is just matching the frequency of a given object. So everything has a given frequency. It's just a matter of matching it. 5, what is the speed of sound at negative 14.5 degrees Celsius? Okay, so you're going to do your velocity equals 331.5 plus 0.6 times negative 14.5. Okay, and this comes out to 322.8 meters per second. Okay, Doppler shift, that is the change in the frequency of a wave caused by relative motion between the source of the wave and the observer. So the big thing there is as it gets closer to you, so as it gets closer, your frequency is going to go up. Okay, and if frequency goes up, pitch goes up. Okay, so that's why it's sounding like it's louder. Okay, and then as it goes farther away, okay, so as it goes away, your frequency goes down. So that means your pitch goes down. 7, what is Mach number? Okay, so Mach is just the velocity of sound at a certain temperature. What is the speed of an aircraft if it's at Mach 2.5? Okay, so if I didn't really give you a temperature here, velocity is normally 340 meters per second. So if I'm doing 2.5 Mach, I'm just going to multiply that by 2.5, and that means I'm going 850 meters per second. Okay, so at a height of 10 meters above the surface of a lake, a sound pulse is generated. The echo from the bottom of the lake returns to the point of origin in 0.140 seconds later. The speed of sound in air is 343 meters per second. And the speed of sound in water is 1,482 meters per second. How deep is the lake? Okay, so if I am 10 meters above the water, okay, so here's my water right here. Okay, so that means I have to go down, and I'm going to go through the water, hit the bottom. I want to know how deep it is, and I'm going to come back up and go back up. So basically the distance it would cover in the air is going to be 20 meters. You have 10 down here and then 10 up here. Okay, so what we're going to do is we're going to find the time it takes from the water. Okay, so basically through the air, from the water back to the source. Okay, so if you want to do that, time equals distance over velocity. I'm just manipulating that velocity equals distance over time equation. So my distance is going to be 20 meters. My velocity of sound is 343. So that means it takes 0.058 seconds to go from the water back to the source. Okay, so and if it takes 0.140 seconds to go through the water, okay, so what I'm going to do is I'm going to take that 0.14 seconds minus 0.058. Okay, so that's the air. So that means the time that it was in the water is 0.082 seconds. Okay. So if I want to figure out how long it takes to get to the bottom, what I'm going to do is I'm going to half that because that's the time it takes to go down and back. Okay, so that's the time underwater is 0.041 when it takes to go from the surface to the bottom. Okay, so if I'm going to define the distance at the bottom of the lake, okay, I'm going to do distance equals velocity times time. So my velocity in water is 1,482 meters per second, and your time is 0.041 seconds. This comes out to 60.76 meters. Okay, so that was probably more of the complicated ones. I don't think that's necessarily going to be on there, but it could be. Okay, but that is everything you need for that. 9, lists 3 applications of sound waves in medical devices. Okay, so that'd be like something like a stethoscope, so like what you hear heartbeats with, ultrasounds, and then also cochlear implants to basically help with hearing. 10, what is the average range of human hearing? Okay, that is going to be 20 hertz to 20,000 hertz. Okay, so anything above 20,000 is going to be supersonic, and anything below 20 is going to be infrasonic. Okay, so 11, what is a sound barrier? Okay, so basically it's just a sharp rise in aerodynamic drag that occurs when the aircraft is approaching the speed of sound. So what it does, it basically creates this giant cone of pressure. Okay, and whenever you break through the sound, that's basically what it's doing, is it's going through that cone of pressure and beating the speed of sound. 12, how many times the intensity of 70 decibels, then 30 decibels? So each time you change by 10, so I'm going to go 70 to 60 to 50 to 40 to 30. So each time you go down by 10, that is a factor of 10. So this is 10 times 10 times 10 times 10. So this would actually be a factor of 10 to the 4th times louder or more intense. Okay, 13, same thing. If you're going from 90 to 50, it's just the same. So you're going 10 by 10 by 10 by 10. So this would also be 10 to the 4th. Okay, what is an echo? An echo is a reflection of a sound from a smooth surface at a distance. Okay, so it is a reflection of a sound from a smooth surface at a distance. Okay, why does sound travel faster in warm air, and why does sound travel even faster in a liquid and solid? Okay, so when you are actually traveling in warm air, the particles are already moving faster. Okay, so the transfer of energy is a lot quicker. Okay, if it's colder, particles are moving a lot slower, so it's not going to transfer that energy as well. Why does it travel even faster in liquid or solid? Okay, the closer the particles are to each other, the more quick it can transfer energy from one to the next. In air, they're very spaced out. Okay, so it's harder to transfer energy. Versus something like steel or water, they're very close to each other, so you can transfer energy quicker instead of trying to reach out and lose that energy. 16, what happens if you force something to vibrate at its natural frequency? That is called resonance. So that's like when an opera singer matches the frequency of a glass. Okay, that creates resonance, and if it's too much amplitude, it'll actually break the glass. Okay, 17, sound travels at the speed of 343 meters per second at 20 degrees Celsius. The wavelength of a sound wave is 131 meters. find the period of the wave. Okay, so I know my wavelength is 1.31 meters. Okay, and I know velocity equals frequency times wavelength. Okay, so what I'm going to do is I know I'm looking for a period. Okay, if I want to find period, okay, basically what I'm going to do is I need to find frequency. Okay, so I know my velocity is 343, and my frequency I don't know, and my wavelength is 1.31. So that means my frequency is going to be 261.83 hertz. So if I want to find period, I know T equals 1 over F. Okay, so T equals 1 divided by 261.83. Okay, and this comes out to 3.82 times 10 to the negative 3 seconds. Okay, or it would just be something small, so it would be 0.00382. So whichever one works for you. Number 18, when an automobile moves towards a listener, the sound of its horn seems relatively, okay, so when it's moving closer, this is going to be high-pitched, okay, because the frequency is getting higher. When it moves away, it's going to be low-pitched because frequency is getting lower. Okay, so define light. Light is a small range of frequencies of electromagnetic waves that are part of the electromagnetic spectrum. So basically your visible light. All move at the same speed, so that would be C equals 3.0 times 10 to the 8th. Okay, so basically what changes it is your frequency and wavelength. Okay, so when you think of your colors, you have Roy G. Biv. So red, orange, yellow, green, blue, indigo, violet all have the same speed, but what differs is the amount of the frequency. Your frequency is definitely going to be higher over here, and your wavelength is going to be lower on the right side. And red is going to be one of your lower frequencies and higher wavelength. Okay. 20, how are transparent, translucent, and opaque materials different? Okay, transparent means all light will go through. Translucent means that some of it will go through while some of it will be kept behind. Okay. And then opaque means that no light will get through at all. 21, what is polarization of light? Okay, so it is electromagnetic waves that can be polarized because they are transverse waves. Okay, so this is why sunglasses are polarized, is basically you have lines in your sunglasses that are basically going up and down or left to right. Okay, and what happens is when you have light going in at different angles, so you've got light going in this direction, okay, or horizontal. Okay, I know that's a poor example of being horizontal, but basically what polarization does is it's going to block some of that light. It's going to stop basically stop part of that light getting through, and that's what protects your eyes. Okay, so it'll block certain directions of light. 22, what is a light year? Okay, it is a distance traveled by light in 1 year. Okay, so all you have to do is basically take the speed of light, 3.0 times 10 to the 8th, multiply it by 365 days in a year, and there are 24 hours in 1 day, and there are 3,600 seconds in 1 hour. Or you could have done 60 times 60. Okay, I just saved a little time there. Whatever that is, it comes out to 9.46 times 10 to the 15th meters. Okay, so if I want to know how far it could go in 8.5 light years, you would just take that number and multiply it by 8.5. 23, state the law of reflection. So we've already kind of gone over that. Basically, your incidence angle is going to be equal to the angle of reflection. 24, draw diagrams to show regular and diffuse reflection. Okay, regular reflection is when you have a smooth surface. Okay, so I don't really have to draw this out. Well, I can. Basically, you're going to have pure reflection. Okay, so it's off a smooth surface. Diffuse is when you have something like a jagged surface. So at some points, some of it's going to bounce off, but it may go the other way. It can go off different ways. Okay, so that would be diffuse reflection. Number 25, define refraction. So that's basically the bending of light as it goes from one medium to the next. Okay, so that's why it looks bent. Okay, so when it goes from air to water, okay, it changes velocity, which causes a change in direction. Okay, regardless, on here, frequency does not change. Okay, so you're not actually changing the frequency there. What you're doing is you're just changing the speed and direction when it hits a different wave. Okay, so Snell's law on number 26, that's going to be your Ni times sine of your angle I. So basically the refractive index of your incoming with the angle of your incoming, or incidence, equals the refracted index of refraction times the sine of the angle of refraction. Okay, so 27, we're going to give this one a go. A ray of light traveling through the air of N equals 1.0003 has an angle of incidence 41 degrees upon a sheet of crown glass of 1.52. What is the angle of refraction? Okay, so this basically means that I'm looking for angle R. Okay, so my incoming is from air to my crown glass. So my Ni is going to be my air, which is 1.0003 times sine of the angle, which was 41 degrees. Again, make sure you're in degree mode. And then I went to crown glass, so this would be 1.52. And I don't know my angle R. Okay, so I need to get angle R by itself. So what I'm going to do is I'm going to divide both sides by 1.52. Okay, so that gives me 1.003 times sine of 41 divided by 1.52 gives me sine of my angle R. My next step is going to bring the sine over. When I do, it becomes inverse sine. So what I'm going to do is I'm going to take inverse sine of all of this. So I'd probably solve this first and then put this into second sine. And that is going to equal your angle R. Okay, so again, make sure you're in degree mode. Your angle R should have come out to 25.58 degrees. What is the index of refraction for a material in which light has a velocity of 2.19 times 10 to the 8 meters per second? Okay, so I'm looking for the index of refraction, which is N. And I know this is where you use the N equals C over V. Okay, so this is going to be... this should have been... I'm sorry, going back. This is... Snell's law is actually going to be your N equals C over V. Okay, regardless, these are basically your main equations for this. So we're going to come back down to here. We're looking for our refractive index, which is N. And I know my speed of light is 3.0 times 10 to the 8. That's always the same. And my velocity in the substance is 2.19 times 10 to the 8th. Okay, so again, just make sure these are in parentheses if you're going to put them in the calculator. Otherwise, sometimes you can get the wrong answer. Okay, this comes out to a refractive index of 1.37. 29, what is total internal reflection? When light passes from a more dense to less dense medium at an angle greater than the critical angle, there is no fracted ray, only reflective. Okay, so basically what that means is when you go from more dense to less dense at an angle greater than the critical angle, there's going to be none of the light that goes through. It is going to be purely reflected. 30, what is the critical angle when light is going from crown glass to air? So make sure you pay attention to that. You're going from crown glass to air. Okay, so I'm looking for my critical angle. Your critical angle formula is this. It is your inverse sine of your NR, your refracted, over your NI, your incidence. Okay, so you're going to go refer back to that chart, okay, that has all the index of refractions. So I'm going from crown glass to air. So I'm going to do my inverse sine. So my incoming, my NI is going to be crown glass. That's going to be 1.52 on bottom. Air is the 1.0003. Okay, once I do all that, it should come out to an angle of 41.2 degrees. So if you went past that angle, none of the light is going to go through. It's going to be all reflected. 31, list 2 applications of total internal reflection. Okay, so this would be something like fiber optic cable used in audio systems, or endoscopes. Okay, so that is total internal reflection, so meaning it's coming purely back. 32, what is dispersion of light? It's just basically the separation of light into colors. So this is like your Pink Floyd album. Okay, so when you have the light coming in and you see it hit that pyramid, okay, and then it basically changes into different colors. Okay, that is your dispersion of light. 33, what is the frequency of an X-ray whose wavelength is 0.5 nanometers? Okay, so remember, velocity equals frequency times wavelength. This is an X-ray, so that means it's moving at the speed of light, so 3.0 times 10 to the 8th equals my frequency, which I don't know, and my wavelength is 0.05 nanometers. Watch out, that is 10 to the negative 9. So what you're going to do is 0.5 times 10 to the negative 9. Just throw that on the end there. Okay, get F by itself, and you get a frequency of 6 times 10 to the 17th hertz. Okay, 34, what is the wavelength of a microwave whose frequency is 2.4 gigahertz? Okay, so a microwave, so this is going to be C equals frequency times wavelength. So 3.0 times 10 to the 8th meters per second equals my frequency, so 2.4 gigahertz. Okay, so giga, so this is going to be actually, I think, 10 to the 9th. Okay, so 2.4 times 10 to the 9th. So this is going to be 2.4 times 10 to the 9th for your frequency. And wavelength, I don't know, so you'd leave it like that. So I divide both sides by 2.4 times 10 to the 9th. Okay, so this one I actually did not have on my paper. I did not have this one on mine, so I don't have my calculator with me right now. So just divide both sides by 2.4 times 10 to the 9th, and that would be your answer for that one. 35, how does the ray of light change when it goes into a denser medium? Okay, so basically you have light coming in, and here is basically your normal line right here. If you go to a denser medium, it's actually going to pull that closer to your normal line. Okay, so when you go from less dense to a more dense, it's going to pull it closer towards that perpendicular line. Okay, so that means your incoming angle is going to be a lot higher than your refracted angle here. When you go from when you go into more dense to less dense, so same kind of concept. Okay, you have your normal line. I've got an angle coming in. When you go from more dense to less dense, it's actually going to disperse quicker, so it's actually going to go further out. Okay, so that means your angle coming in is actually going to be less than your angle being refracted. Okay, so I know that was kind of quick on it, so if you need more help on any of this, you can definitely let us know, or you can definitely go back to some of my other videos if you need more in-depth help on there, and then feel free to rewind to this and see whatever you needed, and then let us know if you need any help.